So as we begin our presentation, we just ask that you keep any questions or comments. If you could just please put them into the chat, and we'll try to address as many of them as we can for each group. So just a little summary.
All right. Hello, parents. This was supposed to be, oh, I need to hold this. Hello, parents. This was supposed to be a pneumatically powered V8 engine. It does not work. However, we've got the parts here, and I can explain how it does work. So we've got a chamber here. The air fills this chamber. It gets stopped by these valves, which are opened by some cams that we have over here. It goes through these holes, enters the cylinders, and then it should power an engine. However, there's some issues with valve sealing and parts not fitting as they should, which means that this does not currently work. However, we are working to fix that, just not today.
So we just have a couple of questions for you. So our first one would be like, why did you decide to make this?
Why did I decide to make this? So I like driving. I like cars. I just thought of this one day, and I saw a one-cylinder design on the internet, and I thought making a classic American V8 would be really cool.
And then just one last question from me before we move on. What is the most important thing that you've learned from doing this project?
Most important thing I've learned, well, Matthew and I could probably both speak to this, but well, mainly just focusing entirely on design, focus on every aspect. We overlooked some small details that ended up not being small, just stuff like that.
And then we actually do have one more question from the audience. Are these parts 3D printed? How did you make them?
So we modeled them in CAD, and I'll have Matthew explain more because he actually did the CAD models.
Yeah, so we 3D printed most of the pieces, but some of them are cut out from rubber or just our machine screws that we are using for axles or whatnot. Yeah.
Awesome. Thank you guys so much.
So, wait, do I attach this? Okay, so my device is a bike tachometer. So my device is a bike tachometer, right? So you attach this to your handlebars, and this allows you to measure the speed and velocity of your bike while you're riding. So here we have, so on this ship, we have the internal measurement unit, and that gives us the velocity, acceleration, and angular acceleration using gyroscopes in the X, Y, and Z directions. So first, we have to clean the data. So here, on this graph, we see two functions, a sine wave and a sawtooth wave. And it's a mathematical fact that you can approximate any function using a series of sine waves. And you can do that in reverse. You can take any function, in our case, it's the input data from the accelerometer, and decompose that into sine waves. And our goal here is to reduce noise, right? So we assume that the noise is caused by the high frequency decomposed sine waves. So what we do is we use a low pass filter. So if you look at the top graph, right, the frequencies in the low frequency range stays the same, but the frequencies in the high frequency range decrease. So now we have the problem of orientation, right? If it's just lying flat, like up is the Z direction, this way is the Y direction, and this way is the X direction. And if it's just lying flat, the X and Y, Z directions of the accelerometer match our roll reference frame. But if it's rotated like this, for example, on a handlebar, well, then imagine it's accelerating this direction sideways. In reality, the accelerometer would register this in the Z direction and the up direction. So what we have to do is use the gyroscopes to calculate the yaw, pitch, and roll of this, and that gives us the orientation. And then we use use that to find the rotation matrix to transform the acceleration vectors. and a matrix is just a way of specifying a function that transforms vectors. And once we find the real acceleration, we use that to find the velocity and position, and I send that through Bluetooth to my phone. Here.
So right here we have a model basketball net. I'll just show a long view of this and then I'll pass it off to the creators of this build so they can explain it.
Alrighty, so here's our next project.
All right, so our project is an arcade basketball hoop. It's right here. And so basically the essence is that you're going to be standing right over, wait, is it? All right, so basically the essence is that you basically shoot a basketball at the hoop and it counts the score, and you have a timer that kind of serves as a countdown. So demonstration. All right. So basically the timer is on the right side. You can see it counting down, maybe. And on the left side, there's the score, but it's currently not working. All right. So yeah, the hardest part of our project was definitely the electrical part because it took a lot of coding. And right now, in fact, we're working on it because the code's still faulty.
Thank you so much, Faris. We're gonna show a couple more views of the model. It is a pretty big project, so we'll just go around and show you the different views. And it might be a little bit difficult to see, but next to the nets, we have the score and the time that they were talking about. Overall, really nice project and looks pretty well. You could skip. Yeah. We are pretty busy right now, so we would like it if you could just wait for a bit and we will resume shortly. So right here we have what looks like a greenhouse, and I'll hand it off to the presenters to explain it.
Oh, okay. We're just passing this around. All right. You can point. All right, Thomas, we're talking. She's pointing. All right. You say introduce ourselves? Okay.
All right.
So I'm Zach Dahlem. I'm going to the University of Iowa.
I am Thomas Reese. I'm also going to the University of Iowa.
And this is Maddie. She's going to Purdue. So what we did is we decided that due to COVID, we wanted to make sure that we had a project that we would be able to get done even if we didn't have much lab time. So we decided to grow plants. So here on the right side, we have our base plants. These plants were grown in water. And on the front here, we have our basil. And on the back, we have our mint. So these plants in the middle, we use this fertilizer right here. And we mix it with water. There is no soil in any of this. And on the left plants, we use our MaxiGrow. I don't know if it's hard to see, but our front left plant actually did die. It did not make it all the way. It died after only a couple of weeks. So we think that is because the MaxiGrow was more of a harsh fertilizer, whereas the Florinova was more of a medium fertilizer. So basically the point of this project was to really just see the difference in using fertilizers to just plain water. And if Maddie wants to hold up the plants here, you'll be able to see that the fertilizers actually did make quite a big difference. And then the one on the left, you can't really hold it up and see. However, it is very tangled and it did grow the most. I'll get to you if you want to talk about like the process.
Okay,
like,
so on the left here, left. So there's a greenhouse tent that we bought. This table was sitting in my bedroom next to my bed for about six months. But we decided that we needed to keep the temperature, the humidity, the amount of light consistent. So we decided to keep that in there, and it controlled all of those variables. That's about it. Thank you.
Thank you. Now we'll go back to some of the presentations we.
All right. Hello. I'm Aiden Bowie, and I'm in a group with Helen and Nil, Didi Gururut, and Diana Tarakan. And we tried making a Chicago cityscape to scale that's geographically and physically accurate. Our scale was 1 inch to 90 feet. And as you can see, we tried making this as detailed as possible. We also tried implementing some LEDs, but our code kind of broke down a week before, so.
What was one of the biggest difficulties you faced with the project?
One of the biggest difficulties for us was definitely making sure that all these details were implemented into the buildings. Our computers at home aren't that powerful, so we use a design software called Onshape that helped us collaborate with each other. It's a little hard to see from like that angle, but we have a ton of different buildings with a ton of different like indents and imprints. Another one was definitely the coding. As academy students, we have some experience with hardware, but definitely not a lot of experience doing anything like coding or electrical engineering. Yeah, basically that was like our first try at that.
All right, thank you. We'll move on to the next project now. So right here we have what looks like a model city, and I'll pass it off to the presenters so they can explain.
Do I go first?
Yeah, you always go first.
Let's hold it, right? I don't have to be super close to the mic, right? So up here. Hello, I'm Sebastian, and these are my friends Gael and Brandon, and together we made the model city. So this isn't based off of any real city, so we made up all on our own. And as you can see, on the side we have our blueprint, and this is what we pretty much started with. We have the road layouts as well as a general idea of where our buildings are, as you can see, where they correspond to on our actual model city. And it's built to a 2-to-1 scale, so everything on our model is double the size of on our blueprint. And we try to implement some features from both Chicago and New York, as you can see from the lake, which can be thought as Lake Michigan, the Central Park, and our river running through the middle of the city.
I'm not sure if you can see it from Zoom at home, but all these roads were made using a laser cutter with a very slight etch. All these buildings are made out of cardstock and handcrafted with an X-Acto knife and glue. Every single one of these buildings has a purpose. As you can see, this could be used as a hospital, something as an entertainment center over there, and then an airport closer to that side.
And then next we have the water features such as the beachfront and the river further back. I don't know if you guys can see it, but we dremeled it and sanded it down and made it look realistic, so it slowly slopes down. And then we put paper walls up to hold in the resin, and then casted the resin in, mixed it with some blue dye to make it look like water. And the river has a flowing effect where we added the dye after it started to harden, so it makes it look like it's flowing. Whereas with the beach, it's still water because we added the dye all at once.
Okay, thank you so much. Now we'll be moving on to the next project.
Okay. So, hello everybody. This is my project. It is a radio telescope. So, if you look at my computer here, this graph is coming from the satellite dish here. So if we go around, when I put my hand in front of this, the graph will go down. When I take it off, it goes back up. So my computer is reading from here. And so what the project does is there's two motors on the dish, and I can show that to you moving.
They won't be able to see the screen, but if you just describe what's going on.
Yeah. So the dish will start moving here in a second. So it goes a little bit to the right, and then it takes the data point from here. That goes to my computer. It goes 20 like increments to the right, and then it will move up. There's a motor back here that turns it up, and then it goes to the left 20, and then it goes in like a pattern like this, and the stronger the signal that the dish is getting, the higher number I'll get on my computer, and then I use those numbers and I create an image. I'm not sure if you can see it, but so the image here is a picture of the sky, basically, that I took using the satellite dish. And it doesn't look like much, but if there was a satellite in the sky that like you would use for TV, basically, there would be a white spot, because when the dish is looking right at the satellite, there's going to be a high signal. So that was, I took 2 pictures. There's the other one. Again, they don't look like much, but it's something. Yeah. Is that good? Oh yeah. Do you want any questions? So I saw a video online of someone doing something similar a while ago, and I just had this idea. So yeah.
It looks like it requires a lot of coding.
Yes.
How much did you learn about that?
It takes a lot of trial and error. Stuff never really works the first time. I had to code the motors. I had to code how to get the number, the data point from there, and I had to code to get the picture from the numbers. I actually used stuff I learned in computer science class. So yeah, just lots of trial and error. All right, thank you.
Thank you so much. Virtual groups happen at the end. Let's go.
So what do you want to do?
Virtual groups happen at the end. So we're gonna go down there.
Hello, guys. Ronan, do you want to loop around? Hello, parents. I hope you guys can hear me okay. My name is Kan Oda. Currently a senior, obviously. My college plans for next year are to go to UIUC for mechanical engineering. And here is my WALL-E project. So basically, my primary goal with this project was to recreate WALL-E in terms of both functionality and aesthetics from obviously the Pixar movie WALL-E. The main 3 functionality points I focused on were the tracks, so to help make WALL-E move backwards, forwards, left, right. Second was this compartment here that would open and close to compact trash. And then lastly was for these arms on the side. So in terms of functionality, currently none of it works right now. I guess if I were to chalk it up to something, it would be my poor time management and just, I guess, my overestimation of how well our machines and stuff would do what I wanted to exactly on the first try. So as of right now, nothing works, but my original plan was to have a Bluetooth module that would help drive the motors and everything would operate from my phone. But yeah, in terms of aesthetics, I think I did a pretty good job. And yeah, that's pretty much it. Thanks for listening, guys.
Thank you, Khan. We'll be moving on into the next project now.
So my project was a dice rolling tower to help eliminate any human error since people over time have learned how to cheat on dice games. So the project was about $68 overall, and that was to get the aesthetic appeal to it. But other than that, it was relatively easy. The only problem that I had was with the 3D modeling and the printing of it. Since the modeling, I had to learn a new program entirely that I'd never used before. So it was a good experience for me to get, but it was definitely a challenge to learn an entirely different program that I'd never even had to touch during my entire 4 years in the academy. So the biggest problem with the 3D print was that it had to be done in 2 pieces, which then led to some proportionality issues. But since the first time I printed through it, the top came out to about half the size of the bottom. But once it was reprinted, it came out just how it's supposed to be, and it works well with the more circular dice. Since it was done with the 3D model though, or the 3D printing, there is some like cross beaming within the hole that you put the dice into, which gets more typical 6-sided dice stuck. But when it's done with these kind of dice, so the more circular ones, it rolls them well. And over about 3 hours of testing, I have not seen a singular number come up more than others. So it's pretty good at randomizing them.
Okay, thank you. We'll be moving on to the next project now. Very much, here you go.
Is this good? Yeah. Hi, so we made a coffee table with a mini golf course scene on the inside. My name is Tamara.
I'm Devanshi, and we have a third distance learner named Ayushi. The essential part of this project was to create a mini golf course that could split into 3 different pieces, and we could each take one into our dorm room, and it would essentially turn into a nightstand.
So basically, our biggest issue with the project was just figuring out how to cut glass, because the way that you cut glass is you just score it and you snap it. And a lot of times that can end up with like jagged edges or just uneven, not what you want exactly. Unlike with wood, like you can just use a saw and it's a straight edge and it's nice. But with glass, we had to really work around that and get used to it in the beginning. We also both had to keep safety in mind because we both got a lot of cuts from the glass at first. When it was just first cut before we sanded it and everything like that. But we had to keep in mind to make the edges really straight as possible and the measurements really exact so that when we made the boxes, they were all flush together because glass can't conform to mistakes like wood can. So we just had to really keep that in mind.
Each piece is a theme. So this is Asia, this is America, and this is Europe. So Eiffel Tower, Leaning Tower of Pisa, the Navy Pier Ferris wheel, and then Golden Gate Bridge, and then this is just sushi. We can actually show you how this comes apart. So that's essentially how it looks apart. And when it came to coloring the wood, we looked into staining, but that process would have just taken way too long. So what we did was we took spray paint and we primed the wood, and then we took 3 colors of the actual color and made sure all the coats were even. And then we finished it off with a gloss primer. So that's essentially how it turned out. Thank you.
All right, thank you very much. Brown?
Yeah. Want to do the order of the picture? All right. All right, I'm Shashir Namani.
I'm Rohan Gandhi.
And I'm Rohan Shah. And this is the quadcopter our group built. As you can see, we've also added a camera. This right here is actually the 3rd iteration of our project. The first iteration had 8-inch propellers, but unfortunately with those 8-inch propellers, you cannot generate enough lift to go more than this high. So then on the second iteration, we added 10-inch propellers, but there was still a problem with the brain of the quad. So
basically for the brain of our quadcopter, there's an arrow, but it's facing the wrong direction. And we didn't realize that this would make such big of a difference, but it did. So our quadcopter, whenever you tried to fly it beforehand, it would just flip over to the right and it would just like somersault. And this resulted in a bunch of broken pieces and parts. So what we had to do after that was in our software, we had to change some values to -90 so it actually goes the proper direction.
And right now, as you can see, we're charging our battery and we're hoping we could fly it soon. But before we had it flying, but we haven't charged our battery in a long time, so we have to do it right now. We have our videos going on our slideshow, so hopefully those work. But yeah.
So I know you guys talked about coding and that was one of your big difficulties. Was there any other big difficulty you faced and how did you overcome that, or how would you plan to overcome that in the future?
I think our biggest issue was just that the pieces or that it kept flipping over to the side, and that resulted into a bunch of broken pieces. And that was just the biggest problem because we had to keep on buying new parts and soldering stuff together. Because the propellers, they broke off the antenna of our transmitters, so we had to buy a whole new controller. They also tore up our ESC right here, and this resulted in like the ESC starting to smoke up. So we had to buy a bunch of new pieces. I think that was our biggest issue.
All right, thank you very much. Excuse me.
$10 for the wood and all the fasteners and all the electronics. The biggest challenge was the lifting mechanism. We had to figure out how to replace it in time since we couldn't get it to work.
Hey guys. So, all right. So I'm Fernando, and this is the smart desk. So it's meant to replace a sitting desk with a standing desk, and it's meant to be a lot healthier for you. As you can see here, I'll give you guys a rundown of what's included in my project. So you have the clock that tells you the time, the speaker, this power strip, this wireless charging pad, and this USB hub. So, sorry. So it's meant to replace a sitting desk with a standing desk. So you're standing the whole time. This little stand right here is for the monitor. You put your monitor here and it's supposed to be eye level with you. And then this surface is really sturdy to work on. Some other features it includes, it has some wheels so you can move it around from different locations. It also has some lights so it looks nice, or in case you need like a light if you're working late nights or whatever. I'll tell you guys a little bit more about the process of building the desk. We originally had a lifting mechanism in place with a stepper motor and an Arduino, but we abandoned that idea because one of our group members broke the stepper motor during our testing phase. So we just ended up making a normal desk. We took measurements of all of our heights and eye levels so we can make it so it's like a good height for us, our arms to rest and work, and a good height for you to look at the monitor. And yeah, it's a little simple desk.
All right, thank you very much.
So the basics of our project is an acoustic bass guitar. Due to COVID and time constraints, this has now turned into how to make a bass guitar. Now, we have made the tools to do it, as you can see to the left over there, which basically consists of a steam box. The reason we need a steam box is because to make the side panels of a guitar, you need to bend it, because otherwise you need to carve it out of a big block of wood. As you can imagine, that'd be very expensive and very wasteful. We're high school students. We don't have a lot of money. So we went with the cost-effective way. It just takes a lot of time and a lot of patience. So on the left, you'll see like a plywood box and a pot. That's version 1 of our steam box. The reason we have a version 2 is because version 1 was not able to create steam in a very consistent manner or distribute it in a very consistent manner. So version 2 is a lot more tightly packed. Has a lot less leaks. It's using a wallpaper steamer made by people that know much more than we do, and it can create a much more effective and consistent distribution of all the steam. This allows for the wood to be a lot more pliable and a lot more consistent manner and a lot more effective manner. Now, to the right, there's the mold. The mold is what you bend the pieces onto. Now, the mold is basically a half of the guitar because you make the side panels in 2 pieces. So you use plywood or any other easy and cheap to use wood, and you just make a bunch of layers. Here we have about 5 layers with a 1/2 inch gap in between each of them. Once the wood is actually pliable, you bring the wood onto this, and with a lot of patience and a lot of clamps, you can actually manage to bend the wood onto it. The issue is if you take too long, you can have the wood dry out and it will break. If you do it too quickly, you'll put too much strain on the wood and it will break. In our case, as you can see about right here, I don't know if the camera will pick it up for you, but we took too long, it dried out, and it broke. So that's what creates a lot of the time for a lot of these amateur hobbyists that do this. More often than not, it's not so much the construction of all of these tools, it's more the difficulty of actually managing to use the mold itself very effectively. Now, once you're done with the side panels, can you hold these for me? For the camera? For the camera? I'm sorry? All right.
Wait, what am I saying? What am I talking about?
Explain the body.
Okay, so for the body of the guitar, pretty much you have it in 2 different pieces, and that allows you to cut out semicircles in the middle, which makes it a lot easier to have a circle for the middle of the guitar like normal, and then you glue them together, and that allows you to have the front panel of the guitar. For the back panel, it's pretty much just these 2 glued together, and you cut out the shape where the chalk is. We just didn't have time to do that.
Once that is done, you use what's called aligning. Aligning is effectively a long strip of triangular prisms that go along the seam between the body and the sides. Through that and a lot of wood glue, it's done. Now from there, you carve out the neck from a large block of wood that you can just get from any tree. As we all know, trees are very long, they have a bit of width to them, very easy. You simply just glue that onto the body, you glue a fretboard onto the body, you string it, and you're done. That's the basics of attaching everything to a guitar and then making it.
All right, thank you very much for that insightful project.
Want me to talk right here? Okay. All right. So my project is on identifying exoplanets. So if you've ever heard of the Kepler Space Telescope, it was a telescope that had a mission from 2009 to about 2017 in order to discover exoplanets using the transit method. So basically what the transit method is if you look right here, the transit method, you look at the brightness of an already known star and you look at its brightness over time. And if you look at any deviations of that graph, that means that, hey, there might be a planet crossing in front of it, as you can see from the animation right here. So what I ended up doing is I looked at raw data from NASA's archive and I just graphed that data. And what I did end up doing is from this dip right here, I was able to figure out, and the stuff we already know about that star that it was monitoring, I was able to figure out that a planet exists there, its exact size, its orbital period, and its orbital velocity. So I was able to actually discover a planet that's about the same size as Jupiter, has an orbital period or a year at about 337 days, and an orbital velocity of about 32,311 meters per second squared, or meters per second. So yeah, in effect, this is what NASA thinks that the planet looks like. They figured out the data of it, but I was able to, actually analyze it and do the math and figure out properties of that planet.
All right, thank you so much. You might have already mentioned this already, but what was one of the biggest difficulties you faced with your project, and how did you overcome it, or how would you have overcome it?
The biggest difficulty with this project was not actually the math or the physics part. It was actually like getting this graph and actually figuring out what it actually means. What does this actually say about a planet being there? What does it actually say about that planetary system? And this took a lot of research. It actually took me like weeks to months to actually figure out, how NASA actually did this.
Okay, thank you very much.
Thank you.
All right, so just like a quick summary of it. All right, so hello, welcome to our project. For our senior project, we decided to build a Tetris arcade machine. And we decided to build it because we wanted to build something that was like big, but also interactive. The main part that took most of the time was building the base and the skeleton of the machine. The hardest part of the project was basically the electronics, since we had a bit of a tough time figuring out how to use a Raspberry Pi and how to like configure our arcade buttons and a joystick to like a whole new game, which we had to find off the internet. Other than that, we also had a bit of trouble with our marquee, which Olivia made. It looks really good, but like it took us like almost 2 hours to figure out how to even cut it out of a laser cutter. But in the end, it worked out, and the whole machine worked out, and everything's working. So that is our project.
This is the back. This is just like the Tetris design, since the main big game that we have on here right now is Rip Off Tetris. I don't know if we said that already, but we got that because otherwise we had to pay for the rights for other like typical arcade games. So we just have like a rip off version, and in theory we could get whatever games on it we wanted to, but we don't have that on. And okay, let's go back around the front. Come with me. All right, I'm gonna give you the whole spiel. All right, so this monitor was from Goodwill for $13. What a snag, I know. And then inside this box right here, we have a Raspberry Pi. You can't see it, it's in there, but that's basically like a little computer. And on it, we got a program called RetroPie, so it could play like all the retro arcade machines if we got them. And then we have the buttons, and inside here is also the wiring and stuff for that. So we have like plug in all the wires for that, and then configure the buttons to do whatever we wanted. So we had to program the joystick for up to be up and down to be down, and so on, stuff like that. And so then we have the entire arcade machine. We didn't want it to be too heavy, so we didn't want to build it out of entirely plywood. So we got like this thin, like 1/4-inch plywood to use. And then throughout the whole machine, there's 2x4s built in like a frame and a skeleton structure for the whole thing, so that it could be light and also sturdy. So we had to cut a lot of different angles and stuff like that throughout the whole thing. As you can see on the side, there's like a lot of different angled parts. So we had to cut all those and sand all of those. And then we just used like a nail gun to put it all in once it was all put together. And then up here we have the marquee, like we were talking about earlier, which is just plexiglass. It's acrylic, which was mostly Olivia who worked on that. So you can talk about that if you want to.
Okay, everyone. So the marquee was made by, first I created this Tetris logo design in CAD. Then I forwarded this design to the laser cutter that we have in our very own Principles of Engineering lab. So once I forwarded it, it actually didn't accept my drawing like at all. It took me 20 times. Wrap it up. Oh, okay. So basically what I did was I painted out the parts that needed to be blacked out black, and I put a translucent sheet of paper behind it, and then put LED strips behind it so that it lights up. Thank you so much.
Thank you very much. You're good.
All right, so we are currently getting some pictures of our table here, but I guess I'll start us off. Here's our project. It is meant to be, well, it's meant to be a TV inside of a table. We have a system in there that emulates games on there. So as you might be able to see right now, we have Mario Kart running on it, which you can play with friends and family. That was the whole point, is bringing the family together, being able to play together. Oh.
Oh, yeah, I could talk about the internals. So currently, on the inside of this table, we have, of course, the main television screen that we use to display everything. But as far as actually running the games, we're currently using a Raspberry Pi. That's a small computer about the size of my fist that can be used to do a variety of things. Currently, we are running an operating system known as RetroPie on it, which is designed specifically for emulating older games, such as a Super Mario Kart, which is the one we have currently running, if you want to pan the camera down. So, as you can see, it runs it quite well. However, it does have its limitations. This is a game that was released for the SNES in 1992. As far as trying to get newer games to run specifically on RetroPie, it doesn't work quite as well. For example, if we wanted to load a newer version of Mario Kart 64 was the next generation one, and we have that loaded onto here as well. But every time we try and load it, it freezes on the loading screen. It is also customizable as well. It uses a standard HDMI input, which is just the standard for a lot of systems that are connected to TVs. So if you wanted to connect something a little more modern, like PlayStation 4 or a Nintendo Switch, that would work perfectly fine as well. All right. You want to talk about anything?
So one thing we learned about during this project was definitely how better to communicate. When we were beginning the project, I believe a lot of us had different ideas for what we wanted to do. I myself thought we were just going to build entirely around the table, not have a big table surface like we do now. But during this communication, we were able to cooperate, we were able to collaborate our ideas, and yeah, we just learned how to better communicate. Good? Anything else?
Thank you guys so much.
Thank you, Crap.
So after all these wonderful in-person presentations, we're going to move on to some of our virtual groups, and we're going to be playing recordings of their presentations for you in the next coming minutes. So while we're getting that set up, please just hang tight, and we'll have that for you shortly.
All right, we're gonna be showing the first presentation in a bit.
Anybody else to go over? Hello, I'm Thomas Ashton, and for my senior design project, I decided to build a phone-controlled electric skateboard. After I graduate Bartlett this summer, I plan to attend Bradley University in Peoria, Illinois. I am the only member of my group, so there's not really anybody else to go over. I plan on majoring in computer information systems starting in the 2021 to 2022 school year there. The objective of my project was to build a Bluetooth-controlled electric skateboard. As for its status, well, it's incomplete. The battery ended up not being powerful enough to drive the motor with significant speed or force, and the cables that came attached to to the parts used were too long and stiff to fit under the board, especially without risk of breaking my soldered joints. The project in total cost about $615.92 between the battery, the motors, the electronic speed controllers, the riser pads, the screws, the skateboard deck, the battery, the connection splitter, the XT60 battery connectors, the bullet plugs, the breadboard, the Bluetooth chip, the Arduino, the replacement bullet plugs, a replacement battery splitter, and an anti-surge protector. I ended up needing to replace the bullet plugs and battery splitter because the bullet plugs ended up being an incompatible type, because bullet plugs apparently is the name of 3 separate electrical standards, and the original battery splitter that I purchased was built poorly enough that the plugs were too close together to be able to actually use both ports at the same time. My biggest challenge in building this skateboard was finding accurate and relevant information. If I had been able to find better guides online that went over in more detail what things are relevant to what parts of building a skateboard, then I might have bought a battery with more power or a longer skateboard deck in order to fit the parts under better. But I was not privy to this information before purchase of parts. Now here is a picture of the ESCs hooked up to the skateboard. Thank you for listening to my presentation about my senior design project.
Alrighty, now we're gonna show that drone that we were talking about. They were able to get the drone charged up, and we'll be showing a demonstration of that. Okay. All right, that was pretty cool. We'll resume with the rest of the virtual presentations now.
Name is the Ecosystem Cube. So, including myself, hello, my name is Peter Jose, and I'll be speaking on behalf of my group, and our project name is the Ecosystem Cube. So, including myself, my group members are Brian Spina and Jack Carberry, and together we are PB&J. So, when starting our project in the beginning of the year, we of course had a specific goal in mind. In this case, our goal was to create something that would be able to sustain plant life in an enclosed environment with minimal external support. And as for the status of this project, it is actually complete and fully functional. So when we started creating our project, we of course had to purchase materials. And here you can see a full list of the materials we actually purchased ourselves, as well as the total cost of these materials. So overall, it was about $207 to create this project. And some of this stuff, like the soil pH tester, was mostly used to test different types of soils to see if they would be compatible with the plants we were growing in our cube. But I just want to point out the more important parts of our project, which was the plexiglass, which served as the roof and walls of our cube. This clamp light, which actually served as the heat lamp, as well as the UV light of our cube. So that allowed us to grow our plants without having them rely on sunlight. The water wicks were used so that we wouldn't have to open up our cube to water it. Instead, the water wick would be inside of the cube itself, but also attached to a container on the outside that would be filled with water, so that the water could travel between the cube and the container through the water wick. And because of the water that was entering our cube, we of course needed silicone and epoxy to make this product extremely watertight, to avoid any leaks and messes that could be caused by the water traveling inside of the cube. So when we were actually building this, we found our biggest challenge was just cleanly installing the heat lamp to the top of the inside of the cube. And you can actually see it here. We have a clean sheet of plexiglass on the top of our product with a heat lamp installed from the inside. This top 3 inches of it that's attached to the power cord is sticking above the on the top of the plexiglass, with the bottom half on the inside. So we had to cut a hole in our plexiglass that was a little bigger than those 3 inches that was sticking above. So there was a chance of the heat lamp falling down inside of the chamber where the plants were. So to avoid any bulbs shattering and causing any safety hazards, we had to adhere it to the inside. But we tried using hot glue, but the heat generated from the heat lamp just melted it. So in the end, we chose to use duct tape, as it was the most effective way to ensure our product wouldn't be a safety hazard. So now right here, this is a hydrometer, which this 75 you see right there is actually the humidity of the inside of our product. And the small number right here is the actual temperature of our product. So on the inside of our product. So this was what, if we were using it or someone else was using it, this is what they would use to see the internal environment of our cube. And then they could change the heat lamp settings to change it depending on the type of plants they're growing. So right here, this is a full view of our entire product. This container is attached to the side of our product, and that is actually the water wick you see right now. It is it is both outside and inside of our cube. And the water will travel through the process of osmosis through this wicking material to the inside, which allows us to water our plants without having to open this up. And the water here we've seen to last around 5 to 7 days, so you'd only have to fill this container about once a week. The wood was found in our own garage, and we just put it together and built it into like a base for our entire thing. And it is also sealed with this epoxy and silicone to prevent any water from leaking through. And as for our plants, we have a tomato plant and an asparagus fern, which were both saplings that we put in our cube. So they've actually grown from being very young, and they've grown pretty well. And the middle plant is a salvia plant, which is a full adult that we bought and we put inside of our cube because we want to see if our cube could sustain an adult plant's life. And as of right now, it has been. The plant is growing just fine. It will take some more time to know how it will compete with the other 2 plants when they're trying to grow. But as of right now, our entire product is completely capable of sustaining plant life as well as a diverse amount of plant life. So thank you for listening.
Hi, we're Neha and Chantel, and our project is called Starlite. I'm Neha, and I'm going to be going to Purdue University this year to major in health sciences pre-professional on a pre-dental track.
I'm Chantal, and I'm going to UW-Madison this year, and I will be majoring in pre-pharmacy.
Our project objective was to show a moving color display on a canvas that should light up in different patterns.
Here are the materials we used to create our project and their costs. We used a power supply that was $16.49, LED lights that were $17.99, jumper wires for $9.99, 2 Arduinos that were $13.99 each, and acrylic for $20. Our total was $92.45, and we bought all our materials off of Amazon.
The biggest challenge during our project was creating the code for the light patterns.
To overcome this challenge, we used multiple resources such as videos and our previous knowledge from using Arduino and our past academy classes to help guide us throughout the process.
We started off our project by creating sketches on a software called Onshape, and then we used a laser cutter to print out our designs. We then created the code and LED system that we talked about in our last slide. Different codes create different light patterns, so here are some images of the different patterns we created.
Here is a video of the final product.
Hello everyone, this is our senior tech presentation for our project, the Borat Figurine. My name is Anirudh Ramesh, and I'm going to be studying computer science at University of Urbana-Champaign at the Granger College of Engineering. Our project objective was to create a figurine of the character Borat from the movie Borat: Cultural Learnings of America, and for it to be as lifelike as possible. The status of this project is complete, however non-functional, which means portions of the project were not completely fixed.
Our total cost came out to be $42, but with the exception of the audio equipment, we already had most of the parts we needed. While the materials used for Borat's clothing and the audio equipment were set prices, we had to estimate the cost of the plastic, as an entire spool was not required. Our total cost was relatively low, but it could have been reduced as there were many misprints caused by hardware malfunction, and we also needed to reprint the figurine once.
And this was our biggest challenge. It was Miranda, my dog, eating the Borat figurine. She chewed up the entire torso and bit off the feet. The entire upper body was a mess. She also ate all the clothes, so we had to improvise a bit. And if we hadn't encountered this setback, we probably could have made the figurine a bit closer to what we originally envisioned, but things don't always turn out that way. But in the end, the soundboard worked. She didn't chew that up, just the figurine. And although this was a large setback, overall, it came out pretty well.
As you can see here, there is a 3D model of the Borat figurine. This was modeled on Blender, which is an application that you can use to sculpt and create objects in a 3D plane. Over here, as you can see, the face was modeled using a add-on application called Face Builder, which allows you to place images on a generic face and to sculpt it to your liking. And then we have a fully built torso with legs that are all uniform to create this figurine.
Coming to the end of the presentation, here's a model of the figurine as we originally intended, and the figure on the right is the actual image of the figurine after the dog had its way with it. Overall, it came out good. The soundboard, which is my favorite part, came out perfect. The audio is good too. Clothing wise, again the dog ripped it off, but we made a tribal Borat costume to replace it. Not bad. And overall it was a great project, a lot of fun, a lot of learning, and a lot of new softwares.
Hi, my name is Romy, and
for my senior project, I decided to create a 15 by 15 LED display. So, my name is Romy Lee. I decided to do this as a solo project, and I am going to be an accounting major at DePaul University next year. The objective of my senior project was basically to create a 15 by 15 LED display that can depict animated images. Basically, what I did in the coding was I coded it so that the LED display would display two different images and basically alternate between those two to create an animated image. And I was able to complete it, but in the process of making it, I fried the Arduino board, and so it's completed but non-functional at this time. The project cost, the total was about $60. Basically, the most expensive part about this project was the LED strips themselves, which were about $27. I didn't include the soldering iron price into this because I already had one. And everything else I basically ordered off of Amazon, So the biggest challenge of this project was basically soldering all the wires of the LED strips together so that all the LED strips would be connected. And it was the hardest only because the amount there was and how small the wires were, just for my sake when making it. And here's the picture of the final product. As you can see, the wires are a little bit of a mess, and there were a lot of soldering that I had to do. And yeah, that's basically it. Thank you for listening, and I hope you have a good day.
Hello, good afternoon. I am Kent Lizardo, and I will be talking to you today about my design and tech project that I take part in for most of my senior year. Our project's general topic is tabletop gaming, and my team, which is composed of 5 students here, and here are their prospective colleges as well as their future majors. I'm Kent, and my prospective college is University of Illinois at Chicago, and I plan to take computer science, which goes into my role, which was the software side of the project. So our project objective was to create a budget table that is suitable and practical for virtual entertainment, like gaming. We managed to get it complete and functional for our intended purposes, and here is a list of projected costs for all of our materials that we bought for the project. This includes things that we didn't use and ones that we had lying around. The TV was donated from a project member's neighbor, so although its projected cost is expensive, the on-hand convenience and repurposing of materials allowed the project to actually be somewhat viable for budget. We could have used any other display or monitor with HDMI support, and the Raspberry Pi is budget enough for these kinds of purposes, which make this project actually viable. Here is a list of challenges that we had during the development process. Our biggest challenge in developing this table would be the physical constraints we had while undertaking social distancing. The case was not the same for a research process because online communication is very, very suitable for situations like now. However, physical access is still very limited. This was seen during the final steps of assembling the table together, as we struggled to actually get times where the entire team was together, and due to some of us being distance learning and some of us having different periods. However, the final product came together. On the left, you can see the core of the table actually working. The TV is playing Bomberman with 4 players. It supports 4 players, 4 controllers for each side of the table. Well, you can sit however you want, but it's most comfortable for that. These kinds of games, like the overworld, the top-down type kind of game actually works best for this, but you can basically play any retro game because of RetroPie support. And the right side is the way the table is built, and it looks like a table and works as such. That's pretty much everything. Thank you for watching.
The electric skateboard. My name is Om Patel, and the following year I will be attending UCLA. I'll be majoring in psychobiology on a pre-medicine track. The main objective of this project is that the electric skateboard should be able to move through the usage of a remote control. And the project was completely functional after I completed it. So by using the remote control, the motor was able to run, and when I stood on top of the skateboard, it was able to maneuver around the house. The total cost of the project was around $172. The skateboard for scratch, it cost $20. The ESC control board and the remote, they both came in a package, and that was $43. The battery costs $36, and the motor, which was connected to the wheels, and I had to attach them onto the skateboard after taking the scratch wheels off, that cost $73. And I ordered all of this off of Amazon. The biggest challenge of this project was finding a suitable battery for the skateboard, because since the motor I was using for the electric skateboard is really powerful, it required a really high voltage and power, and the size of the battery had to be big too, 6S LiPo. And the main issue about the batteries is that they are very expensive. And this skateboard, it only lasts a few seconds, because if I wanted to last even longer, I'll need to buy a battery that is at least $100 or $150. And these are the glamour shots. The other one is side view. The other one is the top view. So, thank you.
So my capstone project was basically a pinball machine like the one you would find in an arcade, but it's controlled using Python programming and Arduino, which is basically the PLD, programmable logic device. It's a solo project, so it's just me. I did all of the roles involving building, coding, and electrical engineering. I'm planning to go to college at University of Illinois, and I'll major in computer science. So hopefully this project, which involved Python programming, is also going to help me go in that direction. So the objective of this project was to construct and program a functional game machine, this pinball machine, that uses the Arduino sensors and Arduino concepts. So similar to what I learned in DE and POE classes. So that knowledge is going to be essential here, especially the one regarding the circuits and the PLD knowledge, because that was mainly what I used over here, as well as some VEX knowledge as well, because VEX components are very similar to Arduino components as well. And all the parts of the project are placed in there except for the pop-up sensor, which I wasn't able to find online. So I can say that the project is completely built. All the wooden sidewalls or for the housing are all placed properly. They're screwed in, and they were cut using a table saw and a bandsaw as well as a drill. And this equipment was found in the school's lab. So the whole project, the whole product is built with all of the sensors mounted in the right place. Most of the components work. I'm gonna get into components next, but that's why I would call this a semi-functional product. If you look over here, the push buttons are basically what the user controls, and that controls a solenoid, which basically pushes the ball. The LED is used because one of the solenoids don't seem to work, so I just put an LED in there as a substitute for the second solenoid, just so that the players can actually kind of see how the product exactly works. potentiometer just to change the intensity in case, you know, you're very close to something. You don't want the servo to go and hit it at a very high pace. So you want to change the intensity to make it slower. Then the user can control that along with the push buttons. So it's a little bit complex. The servo motor basically just hits the ball in random directions. This other potentiometer is used for the ball to hit in order to score points if it's in a certain angle and other buttons are pressed at the same time. Then you can score points, positive or negative, depending on where it is. The LCD, it powers on, but it doesn't really show the exact score in time yet, which is why this is a semi-functional and not completely functional product. On Tinkercad, it does, so I know that the code is fine because I was able to get it to show up on Tinkercad, which is basically a simulation for Arduino. And these additional push buttons just work with the potentiometer to decide what the score the player gets. So scoring basically has the negative sensors in this area and the positive sensors in this area. Such as, you know, one of the push buttons is over here, one of the push buttons is over here. So I did distribute different sensors in different areas. Because of the lack of all the sensors, most of them are positive, which will also help the user win points because the goal is to get 20 points. There's a certain amount of points you get from hitting a sensor. The goal is to get 20 points total, and you want to get it done before the time goes down from 1,000 to 0. This is done using a time variable which has its own loop. This is a snippet from my code, by the way, and the time variable counts down. And you also want to get the score variable, which is shown as score over here, all the way to 20, and that'll either add or subtract from 0 based on what sensors you hit. This is an example of a serial monitor, which basically proves that the product works. You can see that we have sensor values, which basically just show exactly which angle the potentiometer is in and how it changed throughout. So the sensors are getting tracked, whether the buttons are being pressed, so you'll see if it's 0 or 1. That'll all end up to showing a score at the end, so if it ends at 20, like this, then that means that the game is over, and then the Arduino will just stop, and all the components will stop. The project costs, most of the housing materials like the plywood, or maybe even some of the materials to fasten the plywood, basically just cost $30 total. The Arduino and the breadboard and the wires basically they all cost the same. They all cost about $37.28. The input and output sensors cost about $12.48, $58.07 respectively. Some of this I got for free because my school had access to these materials like the breadboard and the wires. Arduino software was free as well. The largest challenge was not knowing what was going on with the LCD. I had to figure out exactly, is it a signaling issue? Same with the code. I was having some trouble with my loop sometimes, but my mentor was able to help me out with those things. Those two things especially, since he was skilled in Arduino. These are just the final pictures of the design. You can see all the components from the LCD display to the potentiometers to the second buttons, which will modify what the score is, to the servos and the solenoids over here, which basically push the ball, and all of the obstacles, which just don't do anything but just move the ball around through the platform. This is the control area. And I'm going to leave this up for a few more seconds so you can see the full view of it.
Hello everyone, welcome to the Humanoid Drone exhibit of this year's Academy Showcase. My name is Sho Takami, and I sought out to build this humanoid drone for my senior year. I aspire to attend and graduate from Northern Illinois University with a double major in mechanical engineering and mathematics, with hopes of specializing in robotics in the future. Now, in essence, this project's objective was for me to create a small flying object with moving humanoid limbs. Yet, as of the time of the showcase, this drone is fully built, but unfortunately, non-functional. This project ended up costing about roughly $400, although about half of that cost accounts for components that were not included in the final product. The main challenge in this project that I encountered was not only building a drone when I had not owned the drone before, but also calibrating the electronic speed controllers with the flight control board. Although the flight control board stated that it has successfully calibrated the speed controllers, they were still not functional, along with the motors and propellers that were integral to making this drone airborne. The left picture reflects my last statement of the board, stating that it has supposedly calibrated or armed the controller, while the right represents the overall drone. Despite not functioning now, I eventually aim to troubleshoot the small error with the flight control board after this showcase, preferably after senior year of high school. That said, I thank you for visiting the Humanoid Drone exhibit.
Good morning, my name is Andrew Tennis and my project is a 512 object-based surround sound system. I am a senior at the Bartlett Academy and I will be attending the United States Military Academy at West Point next year. I am not yet allowed to declare a major until halfway through my plebe year, but I am planning on studying defense and strategic studies and space science or cyber science. So my project focus was to design a high-fidelity 512 or larger channel object-based surround sound system. Basically, in essence, that's 5 surround, 1 sub, and 2 height channels that can then be extrapolated based upon the data to have a sort of customized sound field based upon the data. So you'll, for example, instead of having dedicated audio per channel, the source media could have a 5 decibel sound at 1000 hertz, 45 degrees to the right of center of the listening area. And then that system would adapt that to the current speaker layout. I was able to complete the system. I did have to get a commercial receiver to help me out. I wasn't able to do that digital electronic part myself, but I was able to build out the entire system and all of the hardware, run all the wiring, and it turned out very good. Project cost due to the receiver component and the high price of lumber at this time was about $5,000. If lumber was a little cheaper, probably would have been a little bit less, but at the end of the day, a commercial grade receiver isn't very cheap, so I ended up spending quite a bit on that. The biggest challenge I encountered was the actual crafting, assembling, and finishing of the cabinets. At the end of the day, that was basically cabinetry, which I don't have a ton of experience with, but I did work with some friends and family on making the best products I could, and they turned out very nice. So I'm pleased with the result. Here's 2 images of the final product. On the left, you have the right stereo channel, which is about 4 feet and change tall. It's equipped with an 8-inch woofer and a 1 1/4-inch soft dome tweeter. The center channel has 2 4-inch treated paper woofers and that same tweeter. All the channels have a capacity of about 50 watt RMS and can easily scale up to around 120. If I could change one thing, looking back at it now, I would probably raise the overall diameter of the woofers in the center channel by a little bit. I was initially constrained by size constraints when I was designing it in the beginning, but now that that hasn't been an issue, I probably would have raised the size. I had run into some issues later on with excursion, where on lower frequency incidents such as the THX deep note test, it does over excurse and you get a little bit of crackling from the front channel, but that doesn't occur until about reference level, which is very loud. Thank you for listening to my presentation. Take care.
Hi everyone, my name is Sam Banesh and I am a senior at the Bartlett High School STEM Academy, as well as my group mates Renita Bargis, Jacob Smith, and Alex Natsky-Nyhagen. Now, for our senior tech project, we had the choice to do anything we wanted to do. So we decided to challenge ourselves and create something we have not done before. And we ended up creating a wind turbine generator. Now, this wind turbine generator's objective was to create enough power from wind and generate electricity. And yes, this project is complete and it is functional. The total cost of this project was around $55, and this amounts for all the materials that we have bought, including the ones that we have at home and any extra stuff that we had to get throughout the day. And this includes the PVC pipes, the multimeter, alligator clips, 100-foot wire, tape, styrofoam, DC motors, and super glue. And we also had extra stuff such as Sharpies and pens. So creating this project was pretty simple, but we came across a couple of stumbles, and one really important thing that was not fun at all was when we had to create a hub that stuck to a DC motor. Now, the thing with the DC motor was that the shaft is too small. It's almost a centimeter long, and the hub and the blades are very heavy, as you can see right here. They're 3D printed, thanks to our 3D printers at school. The DC motor cannot technically handle the weightage of the hub and the blades, so I had to create some type of bearing and some type of mechanism for my own household items to hold the hub and the blades. And yes, it worked. And what I found was a small little piece inside a pen, and the hole inside was a perfect thickness for the thickness of the shaft. So when I stuck the pen piece on top of the shaft and I surrounded it with styrofoam and glued it to the hub and just secured it with tape, right, using the orange part right here, thankfully it stayed and did not break. And that was the only really main issue we had. The other issues were the PVC pipes could not fit because we got the wrong size, or the glue was not sticking well enough. But those are things we had to easily fix. In the next clip, I will show you a fully functional wind turbine generator. And I used my hands for one clip, and I also used a hairdryer for the second clip, acting as our wind, because here in Chicago, it's not really that windy anymore. So here we go. Like I mentioned before, I had to use my hairdryer and my hands to create secondary wind. And the turbine didn't really create a lot of electricity, but it still created some. And that's all we needed to know that our project was a success, and it was fully functional. Unfortunately, we could not be there with you guys today at the showcase, but I hope you've had a lot of fun looking at everyone else's amazing talents and creations. And I hope you have an amazing day at the showcase. Thank you for coming, guys.
Alrighty, guys, that concludes our senior presentations. They all did a really wonderful job, and we're so glad that all of you guys were able to come here and see all their hard work over this year. Now, in a couple of hours at around 12:30, we're going to be starting with our junior presentations, and we will be sending out a different link for that. And so if you're interested, please, by all means, come by, stop by, and see what our juniors have done this year as well. Have a wonderful day, and thank you so much for coming.